Can you hear me? Okay, good. So we continue. So now we discuss about polyform. Yeah, of course we know what a polyform is. Okay, so now we just think about the polyform mathematically. Okay, so now we have the complex number z is a plus bi or bj, right? So we can calculate absolute value of z. Okay, we can get the phase angle. Sometimes we say argument. Okay, yeah, for electrical engineer they say phase angle, but for the mathematical, for engineer, the mathematical for application they say it's argument, but it's the same, Yeah. So theta e belonging to real number set. Okay, real number set. So we can get cosine theta, sine theta. Yeah, we just apply the formula. Okay, and we can get z is absolute value of z cosine theta plus j sine theta. Yeah, we discussed before. Okay, so this one we say polyform. Okay, and that means if we have z e a plus jb, and then we indicate z to become z absolute value of z cosine phi plus j sine phi. Okay, so this is polyform. Yeah. And of course, we know one circle, yeah, you get 2 pi. Okay, so if we have k circle, you can get 2 by k. Okay, the case is an integer. Okay, so if here we get a vector z like this, the vector z, and this one is theta. Okay, and then if you and you stay here, and then if you make one circle, you also get the same position. So that means you can say z is the absolute value of z cosine phi not 2 by k, okay, plus j psi phi plus 2 by k. Okay, the same, the same, because when we repeat one circle you get the same position. Okay, and that is the reason here you get theta or phi. Okay, plus 2 by k. Case is belonging to integer set, a set of integers. Okay, okay. So example. Yeah, we have z is this one. Okay, so we find the absolute value of z, argument z, and the polyform of z. Okay, so we take an absolute value of z is the square root of 1 plus minus square root of t squared is 3, so you get 2. Okay, and okay, theta is minus pi over 3. How can you get? Okay, well, easy, very easy. This one is x, this one is y, the first quadrant, the second quadrant, third quadrant, and fourth quadrant. So you get minus 1, sorry, 1, so 1 is here, and minus square root of 3, minus square root of 3, so maybe here, minus square root of 3. Okay, so this one is x. This one is x. Okay, and this one is theta. Okay, so you can get theta is tan to the power of minus 1. Upper side how many? Absolute value of square root of 3 divided by 1. Okay, so that means you can get tan to the power of minus 1 square root of 3, and you get how many? and you get, let me calculate, we get 60 mean pi over 3, but you should remember, you stay here, and we follow clockwise negative, right, to come to z. So that means now theta b, because of the four quadrant, so theta e minus pi over 3 here. Okay, and then plus 2 by k. Okay, 2 by k. Okay, so now we can indicate the polar form. So z is absolute value of z equal to cosine minus pi over 3, right? Plus k 2 by plus j sine minus b by over 3 plus k 2 by. Okay, so this is the polar form, more general polar form. Okay, so of course you can delete. Of course you can delete this one. Then you can get more simplicities of the polar form here. 2 cosine minus pi over 3 plus j sine minus pi over 3. Okay, yeah, this is simple. Any questions so far? Okay, next. Now from, yeah, of course we know, we have, we know two complex numbers. Yeah, we have from z e r with the phase angle theta, and triple e s with the phase angle phi. Okay, so if we have a z times omega, this is r times s, and the phase angle, you take addition, right? Addition, so you get theta plus phi. Okay, so and then you can indicate the polar form of this one. So z times omega e, r times s, right? You get cosine theta plus phi plus j sine theta plus phi. Okay, yeah. Okay, so you can be flexible to use a different representation of complex numbers. Sometimes we use polar form. Sometimes we use different representation of complex numbers. It depends on what kind of questions we have. Okay, and then De Moivre's theorem. Okay, this is interesting theorems. Because, for example, we have r times cosine theta plus I sine theta to the power of n. Okay, n is the power. Okay, the power of n. So you can get r to the power of n cosine n times theta plus plus j or I sine n times theta. Okay, yeah. So the argument of z times omega is the argument of z plus the argument of omega. Okay, so the arguments of z is theta, and the argument of omega is phi, so you get phi plus theta. Okay, now example. We apply De Moivre's theorem. Okay, here. Example here. We would like to calculate 1 minus I square root of 3 to the power of 2000. This is n, right? So n is 2000. Sorry. So you need to modify 1 minus I square root of 3 to become polar form. That means z and cosine phi plus j sine phi. Okay? And we know 1 minus square root of 3i is 2. Yeah, we calculated before. Here. Is 2. Here. 2. Cosine minus pi over 3 plus j sine minus pi over 3. Okay. Yes, yes. Okay, here, here. And then to the power of 2000. Okay, and then we apply the formula. Okay, this one, the polar form to the power of n, AR to the power of n, that means 2 to the power of 2000. Okay, cosine theta to the power of n is cosine theta, cosine n times theta, and that means 2000 times minus pi over 3 plus j minus pi over 3 times 2000. Okay, and when we calculate this one equal to minus 1 over 2, and this one is minus minus j square root of 3 over 2, and then you can get the answer here. Okay, because this is divided by 2. Okay, so 2 to the power of 2000 divided by 2, so you get 2 to the power of 1999. Yeah, this is minus, you take outside, so you get 1 plus I square root of 3. Okay, any questions? So why we know this one? Why we know this one? Why we get this one? Okay, yeah. Sure, but because one circle you get 0 to 2 pi. Okay, so now you will have a minus 2000 pi over 3. Okay, so for yeah, actually we need to modify this one to become the limitation of 0 to 2 pi. Okay, so yeah, so from okay, let me see how can we explain this one. Hmm. Yeah, you can show from the one circle, you get 2 pi. So if we have 1000 circle, you can get the 2000 pi. Okay, so we just focus on pi over 3, right? Minus pi over 3. Okay, we skip 2000. Okay, so we have cosine of minus pi over 3 is 1 over 2. Okay, yeah. So we just skip 2000 because we repeat 1000 circle, you get 2000 by. Okay, yeah. Okay, so next, any questions? We calculate the polar forms examples on radons or the yes, yes, it's up to you. So, okay, but normally we use the reads, but of course you can use radon. Okay, yeah. Okay, so now we have division, right? We have z over to w. So for now, from yeah, of course we know ZAR with theta, and W is S with phi. Okay, so now we have Z divided by W, that means R with theta over S with phase phi. Okay, so that means you get R over S. Okay, this is plus theta. So if you move to the numerator, you get theta minus phi. Okay, so now you get Z over W E R over S with theta minus phi. Okay, so you can get R over S cosine theta minus phi plus J sine theta minus phi. Okay, like this. And similarly, you can get 1 over Z. Okay, inversion of Z. Okay, inversion of Z mean you get 1 over, right, R with theta, or you can get 1 over R, yeah, with minus theta, because this is 0, right? So if you move theta from the numerator to the numerator, okay, yeah, you can get minus theta. Okay, yeah, so here, so minus theta, that means you can get what? So 1 over ZE 1 over R cosine minus theta plus J sine minus theta. Okay, so equal to what? 1 over R, this is R, right? 1 over R cosine of minus theta is cosine theta. Minus sine of minus theta is minus sine theta, or you can say minus J sine theta. Okay, so the same, you know, here, and here. Okay, yeah, finished. Now for end root. So now we have okay. So now we have Z is R cosine theta plus J sine theta, and this is W. Okay, we have two complex number. So if we calculate W to the power of n, okay, so if we apply the Murray theorem, W to the power of n, the S to the power of n, cosine n phi plus J sine n phi. Okay, and then we divide W to the power of n is equal to Z. Okay, so that means Sn equal to R and n phi equal to theta plus 2 by k. Okay, is integer. Okay, so that means S to the power of n is R, so that's S in the n on the root of R. Okay, and you can calculate phi, you know, n phi is theta plus 2 by k, so that means phi is theta plus 2 by k over n. Okay, so now if we have S, okay, that means we have W to the power of n is Z. Okay, that means W W is n root to the power of Z. Okay, and W is what? S cosine phi plus J sine phi. Okay, and S is what? S is n on the root of R, right? Okay, cosine phi is what? Phi is cosine theta 2 k by over n plus J sine theta plus 2 by k over n. Okay, so what is k? K is in the integers from 0 to n to the power n to the minus 1. N is what? N is n on the root, right? The n is the n on the root. Okay, so if you get n, you can get n minus 1. So k is 0 blah blah to n minus 1. Yeah. Example, we would like to calculate 3 on the root of minus 8. So first, step 1, so you need to modify this one because this one is not polar form. So you need to modify this one to become polar form. So minus 8 is A times cosine by plus J sine by. Yes, yes. How can you get this one? Because if we know, if we have 1, so 1 is cosine 0 plus J sine 0. Okay. So if we have minus 1 is cosine by plus J sine by. Cosine by is minus 1, sine by is 0. Okay. So now we get minus A. That means minus 1 times A. You get A. And minus 1 is cosine by plus J sine by. Yeah. Yeah. Very easy. Very easy. So for now, we take this 3 under roots of minus A. That means apply the formula, 3 under root n under root of z. Now 3 under root of minus I equal to n under root of r. So now this is r, right? R. This is r. So 3 under root of 8 cosine theta plus 2k by over n. Okay, so that here you get by, right? By plus 2k by over 3 minus j sine by plus 2k by over 3. And we know k is from 0 to n minus 1 and n is 3, so you get k is 0, 1, 2. Okay, yeah. So here, if k is 0, you get omega 1, k is 1, you get omega 2, and k is 2, you get omega 3. Okay, so as mean, if we indicate the polyform, right, this is real, this is imaginary of what? Of here, objects. Okay, so if k is 0, you get the w1. So this is 1, this is minus, this is square root of 3, this is minus square root of 3. So if k is 0, you get this one, this position, right? This position. And then we continue to follow counterclockwise direction. If k is 1, you get minus 2. Minus 2 is here. Right? And then if k is 2, you get 1 and minus 3, minus j square root of 3 here. Here. Okay, of course, magnitude is what? Of course, magnitude is 2. Okay, so this is the circle. With the radius is 2. Right? Here. Here. So that's mean absolute value of z is 1 plus square root of 3 square is 4. You get 2. Okay. So this is the circle with the radius of 2. So if case E 0, you stay here, right? You stay here. And if rotate, you get next one will be here. And continue to rotate, so you get the next one will be here. And then repeat. Okay, so it's only k is 0. This one case is 1. This one is k is 2. And then repeat. Okay, so one circle, you get 3 points here, here, here. And next circle, here, here, here. So that's in the region we just have k is 0, 1, and 2. We don't have k is 3 because k is 3 will be the same with k is 0, right? 0, 1, 2, and then 3, 4, 5, 6, 7, blah, blah. Okay, so repeat 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the same. So that's in the reason we just have k is 0, k is 1, k is 2. Okay, this. Okay. Any question, please? So far, any questions? Okay, so yeah, we finished the lecture once. Of course, here we have a complex function, but for your reference, okay? When you study communication engineering, I think we will study complex functions. Okay, so now for our complex function we skip. Okay, for your reference. So that is the reasons for the homework. We will we will skip. We will skip complex function. Okay, here we don't have the homework of complex functions. Okay, so from we finished lecture 1, part of 1. So for maybe 5 minutes to do some exercise here. For example, for exercise, I would like to calculate. Here. Okay, 4 on the root of -4. So -4 means 4 goes side by, right? Plus j side by. Do you agree with me? Yes. Okay, so -4 means the square root of 4, right? What else? Goes side by plus j side by. Okay. Yes. So for maybe I move to okay, so maybe I move to here. Okay, okay, yeah. Okay, good. So we answer this one. Okay, so we have -4, right? This one equal to -4 equal to 4, right? Cosine by plus j sine by. Okay, that means you can get any 4. Okay, so we can get square root of 4 with 4, and then cosine by plus 2k by over 4 plus j sine by plus k2 by the 2k by over 4. Okay, this one like this. Okay, you see here. Yes. Okay, so here, so for here, okay, so now if k, k is what? K is a 0, 1, 2, 3, because k is a 0 blah blah to n minus 1. So for -1 is 3. Okay, so if k is 0, you skip this one, so you get okay, for other roots of 4 is 1.41 4. Okay, and then cosine of by over 4. Okay, by over 4 means 45. So you get the root of 2 over 2 plus j. Okay, so we have sine of 45. Yeah, so you get the root of 2 over 2. Okay, so if k is equal, you get 4 other root of 4 cosine of what? Okay, so if KE1, case is 1, so you get cosine of 3 by over 4, right? Plus J sine KE1, you get 3 by over 4, so you get 4 under root of 4. Cosine of 3 by over 4, so you get okay, right? This is by over 4, so this is 3 by over 4. Okay, so you get a minus the root of 2 over 2. Okay, and then plus J. This is sine, this is cosine, right? Okay, root of 2 over 4. This is double root of 2 over 2. Okay, so if KE2, okay, KE2, you get 4 root of 4. This is 2. So you get the cosine 5 by, right? 5 by over 4 plus J sine 5 by over 4. So you get what? 4, 5 by over 4 will be here. Okay. So you get minus root of 2 over 2 minus J root of 2 over 2. Okay. Do you agree with me? Do you agree with me? Any questions? Okay. So, and K over 3. K is 3, right? So you get 4 over 4. Cosine what? 3 times 2, 6. Is you get 7. Cosine 7, 7 by over 4 plus J sine 7 by over 4. You get here, right? Here, right? So you can get a 4 for the root of 4, you get root of 2 over 2 minus J root of 2 over 2. Okay, so now, okay, now if you consider here E case E0 and here case E1, here KE2 and here KE3, okay, and you get the you get this circle, right? So these circles will have radius, okay, we get radius, of what? Of here, right? 4 on the root of 4. Okay, yeah. So for I try again. So we have the polar form of we have the polar form of 4 on the root of 4. This is the real z. This is imaginary of z. Z is what? Z is here. Z is 4 on the root of minus 4, right? Right. So you can get the circle like this, and the radius of the circle is 4 on the root of 4, and we have here is KE0, here is KE1, and here is KE2, and here is KE3, and then repeat. So we have 4 points. Okay, here. So this is the polar form of z. That is 4 under root of minus 4, and this is the this one is the magnitude of z. Okay, yeah. So I think we finished lecture 1. Okay, yeah, and I hope you can understand lecture 1. So we skip complex function. We don't have more time to discuss about complex function derivative of complex numbers. So we have exercise, and we have homework. Homework 1, 2, 3, 4. Okay, now we finish the lectures. So this is the time for TIE. And The time for today will be 11:40 to 12 and 10 p.m. Okay. Yeah, please add TAs if you don't understand clearly about the lecture today. Okay, I hope all of you enjoy it, and see you tomorrow. Let me check. Tomorrow we have the linear algebra class in the afternoon. Okay, Tuesday afternoon. Okay. Yeah, and see you tomorrow. Goodbye. Any questions so far? So if you have any question, just yeah, at the ice. Okay, goodbye. See you tomorrow.